In this video, we're going to analyze perpendicular bisectors in triangles. First, remind yourself what a perpendicular bisector is. Perpendicular means that it's going to cut at a right angle, and bisector means that it's going to cut the segment in half. There are a couple of theorems that we need to go over with perpendicular bisectors. If we know that we have a perpendicular bisector, any point on that perpendicular bisector is going to be equidistant from the endpoints of that segment. So we have the perpendicular bisector line CD here, and point C is on the perpendicular bisector. Therefore, it is the same distance to point A as it is to point B, because it's exactly halfway. We can prove this using congruent triangles, and we would show that CA is congruent to CB. The converse of that is if we know those pieces are congruent, then we know that this line must be the perpendicular bisector. So notice how those are switched from one another, being the converses of one another. Okay, we're going to look at some examples. The first example is with this triangle here. Find each measure. So we're going to find the measure of AB. Well, AB is this segment here. We know from this picture that AC is a perpendicular bisector of BD. Therefore, any point on that perpendicular bisector is going to be equidistant to B or D. And we already know the distance from A to D is 4.1. Therefore, we know AB has to be 4.1. Next, we want to find WY in this triangle. In the picture, notice we have the length of WX is 9. The length of XZ is also 9. We also notice that XY is perpendicular to WZ. Well, because we know that WX and XZ have equal measure, and we have a right angle here, this must mean that XY is a perpendicular bisector of WZ, because point X is equidistant from each one of those endpoints. Therefore, XY bisects WZ, and since YZ is 3, therefore WY also has to be 3. Next, we want to find the measure of RT in this triangle. We notice that RS is the perpendicular bisector of QT. We know that because QS and ST are congruent, and we have the right angle at RS and QT. So far we know that this is a perpendicular bisector. Therefore, point R has to be equidistant from each one of those endpoints. Therefore, RQ and RT have to have equal measure. Then we know the expressions that represent them can be set equal to one another. Then it's just algebraically solving for x, and we get x equals 5. Once we know x equals 5, we have to substitute back in and find that RT is 13. These are examples that I want you to try. You have triangle WZX, and you have 1A, 1B, and 1C to answer. In this illustration, we're going to take a look at the perpendicular bisectors of triangle ABC here. So what I'm going to do is I'm going to make the perpendicular bisectors, and I want you to notice there's this point that each one of those perpendicular bisectors intersect at. All of those purple lines intersect at this point here. No matter where I move those points, you can see they always intersect at that purple point. So no matter where those perpendicular bisectors are, I always have them intersecting at this point. That's actually called something special. So a little vocabulary. You need to know the word concurrent. Concurrent means to intersect at the same point. and the point of concurrency is the point at which those lines intersect. So let's take a look back. The point of concurrency here of the perpendicular bisectors is that purple point. All of those perpendicular bisectors intersect at that point of concurrency. This point of concurrency actually has a special name. It is called the circumcenter. So the circumcenter is that point at which the perpendicular bisectors intersect. Now, the circumcenter is special because it is actually equidistant from each one of the vertices. So in this picture, because P is the circumcenter, from P to A, from P to B, and P to C are all equal distances. Okay, I have another illustration here of the perpendicular bisectors. This triangle, you can see the angles in the triangle, as well as the perpendicular bisectors as the red dotted lines. The circumcenter is point C in this picture. Now, I want to move this around and show you a little bit that no matter what, those perpendicular bisectors are always going to intersect at point C. So I'm going to draw some segments from point C to each one of the vertices. And again, no matter where I move those points, I can see those segments to each one of the vertices, and I can see that all of them intersect at the circumcenter. Now I want to measure the lengths of the segments from the circumcenter to each vertex. So I'm going to measure those. Notice that distance is 4.9. This distance is also 4.9. And this distance is also 4.9. So we can see the circumcenter is the same distance away from each one of those vertices. This is actually going to imply that we could draw a circle around this triangle with the circumcenter being the center of our circle and the lengths to each one of the vertices as my radius. So that's what I'm going to do. I'm going to draw a circle through these points. Notice that each one of those points of the triangle is on that circle. So what we've actually done is what's called circumscribing a triangle. We've drawn a circle around the triangle where the triangle's vertices are 3 points on that circle.